So, in this lecture we shall be discussing some of the recommended practices that are typically followed in an industry which works in the area of digital design. So, it is good to learn this because some of you who may be going to the industry and work in the design area in the future. So, you will be encountering these kind of guidelines there. So, in every industry they have a set of guidelines where they specify that what are the things that you should do and what are the things you should avoid when you are creating a design using some hardware description language. Okay. So, let us see some of these recommended practices. First thing concerns the naming conventions. This concerns file naming. Now, see, Verilog compiler, simulator or synthesizer, whatever you call, they support file names, many of them they support file names which can have arbitrary extensions, not necessarily .v or .verilog or anything. You can have any extension .anything, but let us say here we are specifying a set of typical conventions. So, here you are saying that all the files must have an extension of .v and we must not include more than one module in a file. This is one rule that we should follow. A file must contain only one design unit. You see, this does not mean that you cannot write more than one modules in a file. Yes, you can do. You can write 10 modules in a file, you can synthesize, you can simulate, but these are some of the design practices which is practiced in typical industry houses. Okay. Regarding the namings of the variables, signals or any other object, the conventions are as follows. Names should be composed of alphanumeric characters or underscore. Alphanumeric means alphabets, numerics and underscores. Some Verilog synthesis tools or simulators, they support few other characters also, but this guideline says that you should avoid those, stick to alphanumeric and underscores only, right. And again, even if the compiler supports, so every name must start with a letter, you should not begin a name with an underscore. Third point says the names must be unique irrespective of case. So, what does this mean? This means Verilog is case sensitive, where uppercase and lowercase letters are considered to be different. So, you must not do something like this. Let us say you define one variable as lowercase sum sum, define another variable as uppercase sum sum, and you define another variable which is a combination of this. So, this guideline says that this is not allowed. So, again this is not allowed, it does not mean not allowed by the compiler, it is not allowed by the company, okay? Something like this, right. So, some other conventions, it says parameter and constant names. So, whenever you are defining some constants, so either by using some define statement or using parameters you have already seen, the names must be given in uppercase, for example, pi, pi, d, loy, so that by just seeing a variable name you will understand that whether it refers to a normal variable reg type or var type or it is a constant or a parameter. Just by seeing the variable you can understand. Similarly, signals and variable names, they will be in lowercase. Not only that, names should be meaningful. This is quite obvious. Instead of giving names like A, B, C, D, E, F, you should give names like carry, sum, out, like that, so that the names are somewhat meaningful in the context of the design that you are trying to create. then it says that a constant name must describe the purpose of the constant. Whenever you are defining some constant or a variable name, like say rej underscore enable, something like that. But this can be variable, because the constant I have said that it will be uppercase. So, it can be anything, okay, uppercase or lowercase, but it should be meaningful. So, this repeats not only the variables, names of the modules, the functions and the tasks, they also must be meaningful. So, that just by seeing that module or function or task, you can have a rough idea what it is trying to do, right. So, if a name is a little long, composed of several words, we can use underscores like this, load underscore input. This convention can be followed. Now, see, signals can be either active high or active low. Let us take an example. Suppose I have a register, there is a clear input. So, active high means whenever clear is 1, the register will be cleared. Active low means whenever that clear is 0, the register will be cleared. So, in a design I can use many such signals, some of them can be active high, some of them can be active low. Just as a matter of convention, in order to identify which of the signals are active low, this convention says that you use a suffix underscore b for the active low polarity signals, like clear underscore b. This will tell you that clear is a active low signal, b is a short form for below. Okay. Signals that represent clocks, typically we give names like CLK or clock, but there can be some other signals also. They represent clocks or they are derived from the clock using something called clock gating. Like you can take a clock signal, you can take some other signal line, you can take an AND gate and output will be a so called gated clock. That gated clock can also be used to control or activate some storage cells or registers. Okay. So, such signals you should give an explicit name by suffixing it with underscore CLK, like if the name of the signal is bus, you write bus underscore CLK, indicating that this is also a clock signal. And the last point is quite obvious, unrelated signals must not be bundled into buses. Like let us take an example. Suppose I have a word that indicates an instruction in a processor. So, in this instruction I can have an opcode. So, I can have some fields that indicate registers and some fields that indicate operand. So, what I can do, I can declare them separately, like if opcode is a 6-bit quantity, I can declare them like this. If regs is a, let us say, this is our 6-bit, let us say here I am writing a different way just to show you that I can do this also, register, and this operand, let us say this is a 16-bit quantity, let us say. Now, what I am saying is that you can specify a bus, let us say this is how much, 5, 6 and 6, 12 and 16, 28. So, let us have a 28-bit bus, let us call it bus. So, I can always give an assign statement like this, bus, or you can give any other meaningful name. Instead of bus, let us say, let us give a name instruction, this will be more meaningful. So, assign instruction equal to composition of opcode, regis, operand. This means 3 different things, I am grouping them together and I am referring it to a single entity. this instruction. Here in this point, I mean exactly the same thing is mentioned. It says that whenever you are grouping like this, the signals you are grouping must be related, like here opcode, registers and operand, they are all part of the same instruction, that is why you are grouping them, but unrelated signals you should never group. Okay? Fine. Next, this is very important in a design, comments. So, if you write a Verilog code which is functionally correct, everything is fine, but there are no comments, then after some time you will see that you yourself will not be able to understand that code, you forget about others. So, it is mandatory to have every piece of code very well documented, and that is done using comments. Now, some of the conventions regarding comments are as follows, is that every file you create must contain a header that contains lot of information, and every company has its own conventions. I will give an example later. So, the header among other things must also include the name of the file, such that accidentally the name should not get changed, right. So, it should also contain the highest level construct contained in a file, because you see just in Verilog you can create a design in a hierarchical way, like we took an example of an adder, a ripple carry adder built using full adder, a full adder built using sum and carry and so on. So, that header should also specify what is the level of hierarchy that module or that file is specifying or referring to. Okay? Fine. And of course, it must contain some descriptive note that what the module is actually doing, some explaining the functionality of the module and the parameters used in the module, what are the functions of the parameters, and if there are multiple clock domains, you are using multiple clocks, maybe a slow clock or fast clock, then the header must also specify how many clock domains are used and what kind of clocking strategy is used. Some may be leading edge triggered, some may be falling edge triggered, and some issues regarding critical timing may also be documented, because say for example, when you are designing a module, maybe you know that there is one signal which falls in the critical path. If you make that signal generation slower, your whole system will slow down. So, let that remain documented in the header, so that in the future when someone updates or modifies that module, he will know that well, this is a very important signal, I must not make that signal slower. Okay? That is a critical signal. Fine. Some of the coding style should also be followed. This will of course make the code more easily understandable, and it will be easier to maintain by others mostly. Firstly is that you must give indentation in the code. Indentation means proper spacing in a proper tabular format. So, again I will give an example, because see earlier all the examples that I have shown, their indentation was used. So, I never showed you all the instructions starting from the same column, there will be some spaces, again some spaces, again some spaces. So, just the position of the statement will tell you that under which block that statement is belonging to. So, indentation gives you a very nice visual structure of your whole code, right. Not only indentations, well these indentations are typically, this guideline says you must give 2 to 4 spaces for indentation. Well, and there is also a recommendation, says do not use tabs for giving indentations. Well, many of us have the habit of giving the tab, by pressing the tab some space is obtained to create these spaces. But the problem with tab is that they are differently handled in different systems. In some of the system a tab may be equivalent to 4 spaces, in some other system it may be equivalent to 6 spaces and so on. So, as you move your code across machines, your structure of your code may look different. Okay. And there is another thing here, it says one line must not contain more than one Verilog statements. Now, see, earlier in many of the examples, because of lack of space on the slides, well, I gave some examples like this. Let us say a equal to b plus c, x equal to a minus 5. So, two statements were given on the same line, but this says that you must not do it. This a equal to b plus c should be in one line and x equal to a minus 5 will be in the other line. So, every line must contain one Verilog statement. The next one is very interesting. It says that, well, you can give comments in two ways. Either you can give double slash, which means your entire line is comment, or you can use slash star then comments star slash. This may be a multi-line comment, means say in a code, if you give a slash slash in a line, then the whole line will become a comment. So, again you give a slash slash, this line will become a comment. But if you give a slash followed by a star, then this comment will continue across several lines, then you can give a star slash at the end. So, what this rule says, that to avoid this second kind of comment, you better use this comment, this style, right, because at the beginning you will know from the beginning that, well, this is a comment line, but here say you are not seeing this, you cannot just identify whether this is a comment line or this is part of your code, right, that confusion may be there. So, just use only one line comment using double slash, and just every line of the code must be within 80 characters, so that the line may not spill to the next line. And so, and again another rule says, whenever you are declaring ports, like you are declaring a module whose parameters are a, b, c, typically we specify a, b, c on the same line as in the example that I have shown. But this rule says you must specify them on 3 different lines, a on one line, b on second line, c on third line. Maybe the size or the number of lines of your code will be increasing, but your structure will be very easily visible. You can see that there are 3 parameters on 3 lines, a, b and c. Okay, it will be clearly visible. Fine. Then of course, module partitioning is very quite obvious. So, usually for complex modules, you can divide or split the module into smaller modules and instantiate them into a top level module. That is normally the design style we follow. This is called module partitioning, and this helps in reducing the complexity of design, and because we are handling smaller modules at one time, the chances of errors are also reduced. Now, some of the rules regarding module partitioning says that procedure task functions, wherever it is, they must not access or modify signals not passed as parameter to the module. See, Verilog allows you to access some variables even outside the scope of that task or function, but here the rule says you must never do that. You only access variables that are passed to the function and not other variables. Okay? And if you are using some gated clock or internally generated clock, or if you are using multiple edges of the clock, then the clock generation circuitry must be separated out in a separate module. Okay? This is what this rule says. Similarly, if you have multiple clock domains, like in a design, there is a slow clock and also a fast clock, they must be defined in separate modules, separate blocks. This is important. See, given a design, so our objective is to partition it to smaller design. Okay? Now, the same design, let us say I can also partition it like this. Now, which of them is better? See, you will have to find out how many signals are crossing these partitions. The partition where the number of signals crossing are less, that will be considered to be a better partition, because your number of parameters to the modules will be less. So, your design will be much more structured, and naturally this part of your design will contain most of the self contained code, because they do not have too many interactions with others, right. So, this is one objective of partitioning a larger design. So, the design should be partitioned so as to minimize the number of interface signals, and structural and behavioral code must not be mixed at the same place. Similarly, state machines like FSMs which rely on a clock and asynchronous logic which rely on feedback connections and no clock, they must not again be mixed, they must be put in separate blocks or separate modules, right. Well, some of the general coding techniques are as follows. Like when you are giving a condition, like for example, in the if then else statement, like if some condition you do something, you say A equal to B plus C. But what about this condition? This condition may be the condition that you are checking. Let us say you have declared, let us say, a 2-bit variable, let us call it status. So, here you are trying to check whether status is not 0 0 or not, right. So, which means you are checking whether it is 0 1 or 1 0 or 1 1. So, you see there are two ways in which you can write it. You can either write if simply status. So, what does this mean? Status is a 2-bit number, it will be treated as a number with a value. So, in a 2-bit quantity the value can be either 0 or 1 or 2 or 3, and any non-zero value in the if condition is treated as true. So, if it is either 1 or 2 or 3, it will be considered as true, 0 will mean false. But what it says that you must not use this kind of multi-bit values in status checking. Rather, you use specifically like this, if status greater than 0, then do this. This will also mean the same thing, but here very specifically saying that status greater than 0. You see, status is a 2-bit variable 0 1 2 3 and greater than is an operator. So, if you consider this expression can be either true or false, false or true, a single bit value. Okay. This expression is a single bit expression, but here status was a 2-bit expression. That is why it says the expression in a condition must be a 1-bit value. So, if bus, that same kind of example. So, you avoid this, you rather write bus greater than 0, something like this. Do not assign any signal to x, because you see signals are supposed to be undefined in the beginning, but as computation proceeds you are supposed to initialize them to known values. So, assigning something to x is meaningless. So, you do not do that, right. This is of course clear. Do not infer latches in functions. For multi-way branches you specify the conditions completely. So, a function that is supposed to synthesize combination logic must not generate latches in synthesis. Here operand sizes should match. This is another condition which is specified here. But of course, Verilog supports unequal operand assignments also. Like let us say, suppose I have a variable, let us say 6-bit variable A, and I have another rich type variable. Let us say this is 10 bit variable b. So, inside a procedural block I can write b equal to a. So, the Verilog compiler will accept it. So, it will just assign the 6 bit to the last 6 bits and the higher bits will be set to 0, but this guideline says you must not use this kind of assignment. So, the operands must all be of the same size. So, operand sizes should match, and for complex expressions you use parenthesis to clearly specify the precedences. Now, for synthesis, already in the last lecture we mentioned a few things, some guidelines are to be followed. Like an always block which is meant to design a combination circuit or generate a combination logic must have a complete sensitivity list. So, all the inputs to that combinational functional block must be there in this list, and you should not use more than one clocks inside a single always. This wait and delay statements must not be used. Delay we have already seen, delay is used to specify time delay for simulation, and wait is a statement like this, wait within brackets some expression. This means the expression is evaluated and it is true or false. If it is false, then execution is suspended, whatever statements are after that, those will be suspended, means until it is true. That means, this expression will be continually evaluated, whenever it is true then only that block will start executing. But again this is something to do with simulation, not with synthesis. So, you should avoid this. Conditional expressions, case, if else must be specified completely, otherwise some latches might be generated. Initial statements you cannot use. So, whenever you are instantiating some modules, you must not give expression in terms of ports, like you cannot write in place of some argument, some x plus y or something like that. You can use only single variables for the parameters or arguments when you are instantiating the modules. Okay. And this user driven primitives must not be used, even if the synthesis tool might be supporting at least the combinational UDPs, but these guidelines says you must not use this. And for H sensitive constructs, posage and negage, you use only non blocking assignments. So, the internal wire declarations must follow the IO port declaration, which we already do. So, whenever we declare a module, we first define the input and output signals, then we define the wires. So, exactly that is mentioned here, that the wire declarations must follow the IO port declarations. And this is important, it says use explicit port references in module instantiations. So, I said there are two ways to instantiate, one within bracket you specify the variables in the same order. This is the alternative, you mention the exact name of the variables that was present in the module full adder, and these are the variable names in the current module. The advantage of this notation is that even if you change the order of these lines, still the instantiation will be correct, right. So, it is said that you use this style, do not use the other style, and one parameter per line like this. And it says you avoid case x, because in case x statement this states x and z are treated as do not cares. So, which is not good for synthesis. Synthesis tool might be generating some wrong hardware. And for state encoding you use parameters, which you have already seen. We had used the states S0, S1, S2 instead of calling them as 0, 0, 0, 0, 0, 1, 0, 1, 0. It is always means easy to specify something by names rather than by numbers. Okay. Fine. And it says you use ports only of input and output type. The port in out which you have not discussed in our lectures deliberately. Bidirectional port should be avoided. So, inside procedural blocks, blocking assignment should be used for modeling combination logic only, and for combination logic again you must use the default statement in case. These are some of the guidelines. Okay. So, just a very simple example which shows you the structure of a program. You see the header can be more elaborate. So, this is a very simple example. You see there are so many lines you are using for the header: copyright, some copyright information or message may be there. Then file name, what is the name of this file, what is this type, this is a module, department, author, author's email, because if there is some query you can contact the author. Release history, if there are multiple versions of these, so all the details must be there. What was the version name, which date the version was created, who was the author and what was the modification. Some of the main keywords and some purport description. Here I have given it in a very brief way, 16-bit binary counter. You see indentation, this is the module description where instead of putting them on the same line, we have specified them on separate lines. This is the output, these are inputs, and with all the variable parameter declaration there is a comment which specifies the purpose of that parameter. Then with every block some explanation is there, right, and here also wherever relevant we add comments, clear counter. So, this is just an example. So, with this we actually come to the end of this lecture. Actually, the example that I have showed you is just for you to have a glimpse of the feeling. So, you may think that well, my task is to write the module, to create the design. So, why I shall waste my time in writing the header, creating the comments, but well, this is extremely important. If you write a correct module without any comments, it is as good as useless. No one will be using your module in the future, because in the industry mainly the main emphasis today is on design reuse. Suppose I design some complex subsystem today, tomorrow someone else may be trying to use my design to create a more complex design. So, that person will be trying to reuse my design. So, unless my design is very well documented, this will not be possible. Okay. So, with this we come to the end of this lecture. Thank you.